So let's start with number 8 here, since that was what you already asked for. Folks, you got to be a little quieter so you can hear my voice. It's not 100%. So, how many force diagrams do you need for number 8? Nope. 1 would get you about 2 out of 10. 4. You need 4 force diagrams. You're ready. You're on top of it. Excellent job. So, we're going to do number 8. And so we have our system. And let's see, I just want to get the shape of the system right. Shape of the system is like this. And then we have small box, and then the middle box, and then the other box. All right, let's see. 3 boxes A, B, C are placed on purchase service shown in the diagram. If you push box A, force this, find the contact force between each pair of boxes. So I'm going to write my inertias right in my boxes. So box A has inertia of 5.9 kilograms. So scroll this up just a little bit. So this one is 5.90 kilograms. Terrible 9 on my part. You get the idea. Box B for me is 3.7 kilograms. Box C is 1.5. If I combine those, I get, let's see, 5.2, 10, 11.1. So my system is 11.1 kilograms. Make sure that I did that right. 5.2, 1.5, 5.2. 5 is 10.2 plus 0.9 is okay. Yeah. All right. So I'm gonna remember you don't have to write those inertias in there, but it's not a bad idea. So we push here with a force for me of 8.25 newtons. And we're going to have the weight down. Should we call that the weight of the system or the total weight? Total weight? Okay, so weight total. That would mean we'd have a normal force total. No friction. Alright, so that means this one's going to have the weight of C down, the normal force of C up. Each of these will have their weights down, right? And this one's being pushed with 8.25 newtons. So if that one's being pushed, if A is being pushed, that means A pushes on B. Let's call that force A pushing on B. But that means that B pushes back on A by Newton's third law. So the force of B pushing on A. And if therefore B pushes on C, and if B pushes on C, C pushes back on B. Whoops. This is B pushing on C, and this is C pushing back on B. And of course, we know from Newton's third law those forces are equal in magnitude, right? But opposite direction. And since there's only one force horizontally, that means this whole thing's accelerating. each part of it is accelerated. And that's what you would need to complete for a force diagram for tomorrow for full credit on this problem. So, no, but if this was, well, maybe, but if this was the problem that was assigned for in class tomorrow, and you drew this, you get full credit on your Y. No, I think they're all about the same level, right? It'll be similar to one of the ones you had on this problem set. It's definitely the same difficulty. Okay. On your system? Yes. Not on your individuals, though. Okay. Okay. And that's why I actually drew it up there like that. And I'll actually move it when I do my free body. Because the free body, remember, is just a drawing of the equation. So, but here physically it does matter because it changes the contact. All right, so they want me to find FBC and FAB, right? Yep. All righty. So, if I want to find FBC, I'm going to use box C here. Well, I don't know the acceleration. Maybe I should find the acceleration first, and then I can find out these forces. That would make sense. So I'm going to use the system to find the acceleration. So I'm down into my how. For the system, I always start with my equation. It's a good one to start with since it's the only one I have. And now I'm going to draw, just like yesterday, fill in my equation by drawing it. I have 11.1 kilograms. The total weight down, total normal force up. Yes, this is for the system. And I'm pushing with 8.25 and I'm accelerating. So I've represented my equation now through a drawing, that free body drawing. And now if I'm interested in finding the acceleration here, should I look at the horizontal or vertical forces? What do you think? Look at the horizontal ones, right? Because the acceleration points horizontally. So my first inclination is to look at the horizontal ones. All right? So horizontally, now I'm going to just fill in that equation again, but this time using numbers rather than using a drawing. Okay, if I call to the left positive, is that okay with everyone? Because everything points that way, so all of my forces that I have to enter are 8.25. That equals my inertia, which is 11.1 kilograms, times my acceleration, which I don't know. Oh, so I could do a little math. And get a value for acceleration, which would be, let's see, 8.25 divided by 7.43? No, 0.743. 0.743 meters per second squared. So now I've found my acceleration, which they didn't ask me for, but probably is going to be useful. So, let's see. Which one do you guys want to try to find first? The force of B on A or the force of B on C? The AB one first? Okay, so I've got to use box A, the force diagram of box A, to find that then. So I'm going to start with, let's see, I think I'll start with my equation. So, page, so I'm using box A here. I'm going to start with sum of the forces equals MA. Why I'm over on the side, I don't know. Do my free-body diagram to fill in that equation. See my inertia, 5.9 kilograms. Force normal A, weight of A, 8.25 newtons. Force of B on A, and 0.743 meters per second squared. I think I got everything for my force diagram. I'm doing box A, so it'd be my inertia for A. I could do box B, but there's two forces on it that I don't know either right now. So. Alright, so now I express it mathematically, with numbers rather than pictures. I'm again going to take the left as positive, just for consistency. So I've got 8.25 newtons minus FBA equals, and again, I'm just doing horizontal. My inertia, 5.9 kilograms times 0.743 meters per second squared. And, so a little rearranging, right? FBA equals 5.9 kilograms times 0.743 meters per second squared. Oh, that should be negative. I'm going to back up 1 second here. I'm going to have 8.25 minus that equals FBA. Sorry. I just needed to bring the FBA over here in this part over there. Make sure you see that. So, let's see. 8.25 minus, parentheses, 5.9 times, so there's that number. Made myself a little typing. Close parentheses. Enter. And I get 3.86. So I get an FBA of 3.86. Yes. I got 3.86. Now I need to do the other one. And I would say let's use box C to do that one. Less forces again. Right? So leaving it, I start with my equation. And we're going to do box C this time. So I do my three-body diagram again. Weight of C, normal force of C, and then force of B on C. What was its inertia? 1.5? Okay, thank you. 1.5 kilograms. And then the only other thing I need to have on here to fill out my equation is my acceleration, which is 0.743 meters per second squared. Well, remember, it's a vector, so I can move wherever I like as long as I keep its direction constant. So I had it pointing to the left. And it doesn't matter if I have that, the tip of the arrow or the tail of the arrow on the center. I tend to put the tails. Sure, on you're right, on box B, but I don't care about box B. I'm only looking at box C. Yeah, well, just to make life simpler, right? So I only have one force here, FBC. That equals my inertia, 1.5 kilograms, times my acceleration, 0.743 meters per second squared. Well, and if I pick box B, I would have two. Sure. Because of Newton's third law, for reaction is an equal and opposite reaction. So box B pushes on box C. Box C pushes back on box B with the exact same amount of force. Yes. Yep. Right, you know that they're equal and opposite. Yeah. All right, so we're going to start in on number 9 here. In number 9, we have an Atwood machine. And so we have the system, and then we have the two bodies in the system. And this is one we did on the other day. So what I'm going to draw, and I'm going to draw it kind of weirdly here, I want to draw it without worrying about the pulley. The pulley is light and frictionless. So here's my system. It's the two things together, not worrying about the pulley. And then I'm going to have the one mass with its cord, and I'll have the other mass with its cord also. So I'm going to end up with 3 force diagrams here. Let me get some. Let's see. A has 2.65 and B is larger, so this is 2.65, and my larger one, maybe I should draw it larger. This is A and this is B, is 6.45. Now, which way is this going to accelerate? Clockwise, yeah. A will go up, B will go down, so we got to think of a direction that incorporates that, and we can call that clockwise. So that's where our acceleration, I would actually draw it on this one like this. And one thing I want to keep in mind is the weight of A and the weight of B are actually in opposite directions from each other. And that's the weird thing about this force diagram, is that those two in concept are in opposite directions. So you've got the weight of B here in one way, in one direction, the weight of A in the opposite, and then, oops, it should touch. Here we have the force of tension up, and the force of tension up here. And in this case, the acceleration would be upwards, and here it would be in that same direction. But when we draw it, it looks like they're in opposite directions, those two accelerations. But because we're going around this corner, they're in the same direction. So when I draw my free bodies, I may modify that. So we'll continue this one after lunch. All right? All right, so starting back in on this one, number 9. Right? We have all our force diagrams done. What do they want to know? They want to know the magnitude of the acceleration, the magnitude of the tension, through what distance will the two objects move in the first 4 seconds of motion. Oh, good. So a little kinematics review there as we approach the midterm. That's good. So, acceleration. Probably use the system, right, for the acceleration. That'll make, that will be, I think, easier since then we'll know more. So, start with the system. Sum of the forces equal to MA. And then we'll draw the input from the system. Now here's the point that some people might be a little confused about. Remember that FGA goes in the opposite direction as FGB. So I'm going to draw those in opposite directions. And then my acceleration go that way. So my attempt is to kind of make more sense rather than how my force diagram looked. And let's see, 2.65 plus 6.45 would give me 9.1. Yeah, 9.1. So the inertia here of my system for me is 9.1 kilograms. All right. And now that I've drawn my equation, I can write my equation. Let's call to the, we're going to call to the right here positive. So I have FGB minus FGA equals my inertia, 9.1 kilograms times A. Yes. Yeah. Because that's the inertia of the whole system together. And now I want to find A, so I know the weight of B is the mass of B times the gravitational field minus the mass of A times the gravitational field. That's going to equal the 9.1 kilograms times the acceleration. So, let's see. My math was, I've got 6.45 kilograms times 9.80 newtons per kilogram minus 2.65 kilograms. Did I get this right? Yeah. Times times 9.80 newtons per kilogram. If I divide all that by 9.1 kilograms, I get A. That's the mass of block A. Basically what I'm doing is the weight of block B minus the weight of block A is the inertia of the whole system times the acceleration. And then I find a value here for A now. Then, well, let's see. Maybe I should find that value. Parentheses 6.45 times 9.8 parentheses minus 2.65 enter. All that divided by 4.09. So I get 4.09 meters per second. Now they want me to find the tension in the string. So I can use either one to find the tension. Anyone have a preference? I'm going to use the 2.65 then. I don't know why, I just feel like it. So, start with my equation as always. Draw my equation. 2.65 kilograms. FT, this is my block B, I believe. Maybe I'm wrong. Let's see. Yeah, this is my block A, you're right. I think I need to recalibrate the board. So now that I've got my equation drawn, I'm going to write my equation. Ft minus FTA equals my inertia, 2.65 kilograms, times my acceleration, 4.09 meters per second squared. So Ft will equal whatever that is, 2.65 kilograms times 4.09 meters per second squared, plus, oh, that's the weight, so that would be MA times G. Yeah, I definitely need to read something here. So, you see what numbers to substitute in there, right? Yes, no, maybe. Okay. Check that you used your numbers, not mine. Okay. No, let me double check mine. I'll pause for a second. Then they want to know, through what distance will the two objects move in the first 4 seconds of motion? So for that, we need to remember our way back and use that D equals D naught plus V initial T plus 1/2 A T squared. The initial 0, D naught is 0. We're looking for D, so D equals 1/2. We have our acceleration, 4.09 meters per second squared. We have our t, our time, which is 4 seconds. So 4.0 seconds. And square that and find the displacement.